Welcome back to JEE Blunders, where you learn the don'ts first. So today we'll be starting with a new topic, rotational mechanics. A uniform rod of mass m and length L is hinged at one end and lies on a horizontal frictionless surface. A force F is applied perpendicular to the rod at one end. So find the acceleration of center of mass of the rod. So basically we have to find the acceleration of this point, which, if it's a uniform rod, is at a distance L by 2 from one end. Okay, so we'll start with the free body diagram. So we have F, which is the force, external force that is applied, and we're going to have the hinge reactions. So remember that we are drawing the free body diagram of the rod, which means the hinge is external to the rod. So we have the hinge reactions. So in general, the hinge reaction can be in any direction. So we have two components. Let's call that Hx and Hy. So I'm just arbitrarily assuming directions. So we'll get to know the directions as we proceed. Right? So just looking at the center of mass of the rod, we know that it will have a tendency to execute circular motion. Right? So there must be some force that contributes to the centripetal force. And in this case, that's the horizontal component of the hinge reaction. So we can say that Hx equals m L by 2 times omega squared, where omega is the angular velocity. But we're assuming that the rod is at rest initially, right? So omega must be 0, which means the whole thing is 0. Hx is 0, right? So we have used Newton's laws in one of the directions, in the horizontal direction. So in the other direction, we have F minus Hy is m times the acceleration in that direction. So let's call this x and y. So this is the y component of acceleration. And if we also use the rotational equation, so we can say that the torque about, let's call this point O. So the torque about point O is the moment of inertia about point O times the angular acceleration. The torque about point O, there's no torque due to the hinge reaction. So it's just F times L is the moment of inertia about the hinge. That's ml squared by 3 times alpha, right? And we also have ay equals L by 2 into alpha. So the rod is in pure rotation about point O. So that's how we get this equation. So we have 1, 2, 3. So the unknowns are Hy, so that's one unknown. Ay is another unknown, and alpha is an unknown. So we have 3 equations and 3 unknowns, so we can solve this. Okay, so F minus Hy equals m. Well, let's actually solve for 2 and 3 first. Or actually, let's just substitute it here. M times L by 2 into alpha. And alpha is nothing but 3FL by ml squared, right? Okay, so all of this cancels out. So we have 3f by 2 left over here. So Hy is f minus 3f by 2, that's minus f by 2. Hy is minus f by 2. Okay. Something's not right. Anyway. Okay, Hy is minus f by 2. So ay Ay is F minus Hy by M from equation 1. So F minus Hy is 3F by 2, so by M. So Ay is 3F by 2M. So and it seems like this is our answer. Although something's not right because Hy, well, let's actually draw the free body diagram. Just make sure we're doing it correct. So we have the rod, right? We have the rod, and we have F, Hx is 0, and Hy is minus F by 2. So it's F by 2 in the direction opposite to what we assumed. Something's not right because the hinge is supposed to be restraining the motion of the rod, isn't it? Instead, somehow it seems to be supporting motion. If you actually think about it, let's say we have a rod, same mass m, same length l, and if I just apply a force F at one end, mass m, length l, it's going to experience an acceleration of F by m. And with the hinge, the rod's experiencing an acceleration of 3F by 2m, which is more than F by m. Something is not right because the hinge seems to be pushing the rod, it seems to be accelerating the rod more than the case without a hinge. Okay, I am not able to think of an answer for this, but if you guys are able to crack this code, definitely do let me know in the comments below. See you soon.